Welcome back, everybody, to another deep dive. This time we're diving into an essay all about something called Feedforward Neural Networks, or FNNs.
Yeah, and the essay is by Jörg-Owe. And I think you'll find this interesting because whether you know it or not, FNNs are something that's probably having a big impact on your life.
You know, that's actually a good point because I was reading through the essay and Schneppat even calls FNNs the backbone of AI. So that means they must be pretty important.
Yeah, that's true. It really is the kind of underlying architecture for a lot of different AI applications that we see and use all the time.
Okay, so maybe let's start with like a basic definition here. What exactly is an FNN?
Well, think of it this way. So imagine a one-way street for information.
Okay.
So it starts with some input data, right? It could be anything. It could be the pixels in an image or some text from a book or even financial data.
Yeah.
And then that data flows through a series of layers. Okay. So each layer is performing some calculations on that data and then passing it on to the next layer.
Okay.
And then finally it reaches an output layer.
I see.
And that output layer gives us a result. Like say it could be identifying what object is in that image or translating that text or predicting tomorrow's stock prices.
So it's almost like a chain reaction of sorts. It's like one thing leads to another, leads to another.
Exactly. It's a very specific path that the information follows.
I see.
And that's why it's called feed forward, because the information only moves forward. It never goes back.
So what makes an FNN different than like any old computer program? I mean, a computer program can take an input and spit out an output too, right?
Yeah, for sure. But here's the key difference. An FNN learns from data.
Okay.
So instead of being explicitly programmed with a set of rules to follow, an FNN is trained on massive data sets.
Right.
And so it's actually adjusting its internal parameters based on the patterns it finds in that data.
Oh, well.
So this learning process is really what makes FNNs so powerful and why they're at the heart of so many AI breakthroughs these days.
Schneppat mentions these things called hidden layers in an FNN. What exactly are those?
Well, you can kind of think of the hidden layers as a black box, right?
Okay.
We know the data goes in and some calculations happen and then a more processed version of the data comes out the other side. But what's really happening inside those hidden layers is pretty complex.
So if we break down the structure of an FNN a little bit more, we have the input layer, which is taking in the raw data.
Right.
Then it goes through these mysterious hidden layers, which are crunching the numbers and finding patterns.
Yeah. Exactly.
And then it gets to the output layer, which gives us our final prediction.
Right. And it's the hidden layers that do the heavy lifting when it comes to learning. They are the ones that are adjusting their parameters based on the data. It's kind of like they're building up an understanding of the relationships in the data.
That's pretty cool. So how do you actually decide, like, how many of these hidden layers to use and how complex each layer should be?
Yeah, that's a good question. And to be honest, it's one of the biggest challenges when building an FNN. There's no easy answer or rule of thumb. It really depends on the complexity of the task you're trying to achieve. It's kind of like deciding how many gears to put in a car.
Oh, I see.
Right? Like a simple car that's just driving around town doesn't need a ton of gears. But a race car that needs to perform at high speeds needs a much more complex transmission.
Okay, so you're saying the more complex the task, the more hidden layers you probably need.
Yeah, generally speaking, that's a good rule of thumb.
Now, Schneppat also talks about these things called activation functions, which sounds pretty sci-fi. What are those and what do they do?
Right. So activation functions are kind of like the secret sauce of an FNN. They're what introduce what we call nonlinearity into the network. And without them, an FNN would actually just be a bunch of straight lines.
Straight lines.
Yeah, incapable of modeling all the complex curves and patterns that exist in real-world data.
So what does that actually mean? Like, what's an example of how an activation function works?
Okay, so imagine you're trying to teach an FNN to distinguish between cats and dogs.
Okay, yeah.
So the features it extracts from the images might be things like pointy ears or fluffy tails, right?
Right.
A linear function might struggle to separate those categories effectively because some cats have fluffy tails and some dogs have pointy ears.
Oh, that makes sense.
But an activation function allows the network to draw more nuanced boundaries between those categories, so it can kind of account for those exceptions and those overlaps.
So it's like you're saying it adds some flexibility, like some wiggle room to the decision-making process.
Exactly. Yeah, it's a way to kind of capture the nuances of the real world.
I see. So without activation functions, FNNs would be pretty limited in what they could do.
Oh, yeah, definitely. They'd be stuck in a world of straight lines and wouldn't be able to handle most of the problems we throw at them.
So it sounds like these activation functions are pretty important.
Oh, they are. They're really what allow the network to learn those more sophisticated relationships between the input and the output.
Yep.
And, that's ultimately what makes it capable of solving those complex tasks. It's funny, though, because when you think about it, like an FNN, it's not like traditional programming at all, where you write out specific instructions.
Right, yeah. Schneppat talks about this. He says that FNNs are more like trained than programmed. So how does that actually work?
Okay, well, imagine you're teaching a child to ride a bike.
Okay.
You don't give them a textbook, on physics and biomechanics. You kind of just let them try, and they fall down, they get back up, they adjust, and gradually they get better and better.
Right.
Yeah.
Well, training an FNN is kind of similar to that.
So what's the bike in this analogy?
I guess the bike would be like the task we want the FNN to perform.
Right.
So like recognizing an image or predicting that stock price. And we train the FNN by feeding it huge amounts of data.
And that would be labeled examples of images or stock prices from the past and things like that.
And then what?
With each example, the network makes a prediction, compares it to the correct answer, and then adjusts its internal parameters to kind of reduce the error.
So in a way, it's almost like learning from its mistakes.
Yeah, exactly. It's constantly refining its approach based on the feedback it gets.
That's really cool. And now Schneppat mentions these terms, forward and backward propagation. What are those, and are they part of this learning process?
Yeah, definitely. So forward propagation is basically like the initial attempt to ride the bike. So that's when the data flows through the network and it produces an output or that prediction. And then backward propagation comes in, and it's more like analyzing, why you wobbled or why you fell off the bike.
Oh, yeah.
So the network calculates the error. That's the difference between its prediction and the actual answer. And then that error is used to kind of go back and adjust the connections between the neurons, and that makes it slightly more likely to get it right the next time.
So it's a constant process of trying, evaluating, and then refining.
Exactly. Yeah. And this actually happens millions, even billions of times during training. So you can imagine the network is constantly tweaking its parameters until it becomes really good at whatever task it's been given.
But this training process, it's not always smooth sailing, right? Mm-hmm. There are some challenges and some potential pitfalls here.
Right. Yeah, there definitely are. Well, so one of the biggest dangers is something called overfitting. And maybe we can go back to our bike analogy here.
Okay.
Imagine that child learning to ride the bike, but they only practice on a perfectly smooth surface.
Okay, yeah.
So they might seem like an expert on that surface.
Right.
But then you take them out to a bumpy trail and suddenly they're crashing all over the place.
Oh, I see. So they've learned the specifics of that one environment way too well, but they haven't really learned the underlying skill of balance and coordination.
Exactly. And the same thing can actually happen with FNNs.
Really?
If they're trained for too long or on data that's too similar, they can start to memorize the training examples instead of learning those general patterns.
So like a student who just crams for the test, but then can't actually apply the knowledge in the real world?
Exactly. So they might do incredibly well on the data they've seen before, but then they'll fail miserably when they're faced with new data.
So how do you prevent that? How do you prevent an FNN from becoming like an overconfident, overspecialized bike rider?
Well, luckily there are a few techniques that we can use, and one of them is called regularization, and that basically encourages the network to kind of favor those simpler solutions.
Okay.
It's like telling the kid, don't just memorize this one path, focus on developing your balance and your coordination so that you can ride anywhere.
So it's about finding that balance between learning the specifics and also being able to generalize to new situations.
Yeah, exactly. It's about finding that sweet spot where the FNN is both accurate and adaptable.
That makes a lot of sense. So we've talked a lot about what FNNs are and how they learn, but I'm really curious to hear about some real world examples of this. How are FNNs actually being used out there in the world?
Yeah, well, Schneppat actually gives some really mind-blowing examples. And, it's pretty amazing to see the impact that FNNs are already having on all these different fields.
So we've talked a lot about what these FNNs are and how they actually learn, but I think the most interesting part is how are they actually being used? What are some real world examples where we see these things in action?
Yeah, Schneppat has a whole section in the essay about, real world applications. And one that really stood out to me was in medical diagnosis.
Oh, wow. That sounds promising. What kind of impact are they having there?
Well, researchers are training FNNs to analyze medical images.
Okay.
So things like X-rays and scans. And actually, they're finding that FNNs can sometimes detect signs of disease that might be missed by the human eye.
Oh, wow. So it's like having a second set of eyes, almost like a superpowered radiologist.
Exactly. And, there's even work being done on FNNs that can predict patient outcomes.
Really?
Yeah, based on like their medical history and their genetic data.
So we're talking about potentially life-saving applications here.
Oh, absolutely. Yeah, early and accurate diagnosis is really critical, for effective treatment.
Right.
And FNNs are proving to be incredibly valuable tools in that regard.
And it sounds like the applications go way beyond medicine, too.
Oh, yeah, for sure. Schneppet talks about how FNNs are being used in finance.
Okay.
To predict stock prices and assess risk and even detect fraudulent transactions.
Wow.
And then in marketing, they're used to personalize those recommendations that we see online, target advertising and optimize pricing strategies.
Yeah, it's kind of amazing to think how much of our digital world is already being shaped by this technology.
Yeah.
Like, we probably interact with FNNs on a daily basis without even realizing it.
Oh, yeah, totally. And, it's just going to keep growing. As the field continues to evolve, we can expect to see even more like innovative applications emerge.
It makes you wonder, like, what's next? What other problems are we going to be able to solve with FNNs?
It's exciting to think about. But Schneppet does point out that there are still some challenges, with building these things. Like, it's not all easy.
Right. Well, what are some of those challenges?
Well, one of the biggest ones is just the complexity of it. So, choosing the right architecture for the network and then tuning all those parameters during training, making sure that it generalizes well to new data.
Right.
All of that requires a lot of expertise. It's not just a matter of plugging in some data and letting the magic happen.
So it's like there's still a human element here. Like, we still need people who understand how these things work and how to build them effectively.
Oh, yeah, absolutely. There's a lot of art and skill involved in building and deploying these FNNs, but the potential rewards are enormous.
So where does Schneppet leave us at the end of this essay?
He makes a really strong case for the transformative power of FNNs. He believes they have the potential to revolutionize countless industries and solve some of the world's most pressing problems. And, I have to say, I think he's right.
Well, I think you're right, too. And I definitely think this deep dive has given us a lot to think about. FNNs are clearly much more than just a buzzword.
Yeah.
They're a really powerful technology that's already having a huge impact on our lives.
Yeah, and I think it's only going to grow in the years to come.
Well, thanks for joining us on this deep dive, and be sure to check out Schneppet's essay if you want to learn even more. It's a really fascinating read.
Yeah, definitely check it out.
And until next time.